So what we have is, if I look at what the derivative really means, when I'm talking about the derivative, I'm looking at the rate of change that occurs at any particular value at a function. And so if I just draw my an arbitrary function, and I'm interested in the slope of this function at a. So what is the rate of change at a? So it's easy enough to compute f at a. That's just plugging in the number for our function. But how do we get the slope? And so the rate of change. So the way we're going to do this is we're going to take advantage of the notion of limits. All right. So we're going to set up a secant line. And if we look at any particular value of x, we can note that the average rate of change between those two values from a to x, the average rate of change is just going to be how f changes divided by how x changes. So this is exactly the definition of the slope of a line that we had, where it's y2 minus y1 over x2 minus x1, except now I'm just using the function. And I've left it as f at x because x can be any value that I choose, and so I'd get the average rate of change between a and whatever this value is. And so what I want to do with this is I want to define the difference between x and a as h, and so that denominator is going to be just h, and all that means is, you know, how far apart are the two numbers that I'm talking about. And then instead of f at x, I can say it's a plus h, right, because that's what will give us x. So if I take a and add h to it, then I get x. And so I can restate my average rate of change then as f at a plus h minus f at a over h. And so what I want to do now with this secant line, this lower one right here, is if I reduce h, and so what I'm doing is I'm bringing x closer and closer to a, what's going to happen is that my secant line is then going to become a tangent line. And so that will be the line that shares the same slope as my function at point A. And so that's all a tangent line is. It's a line that the tangent line at that point intersects the graph, but also has the same rate of change of the graph. And so if I state this in terms of limits then, I can then define my instantaneous rate of change. The rate of change at exactly a is going to be the limit as h goes to 0 of this difference ratio. And so you can see why we've been dwelling on finding limits of ratios where it's going to be 0 divided by 0, because very quickly you can tell that the difference in the function as h gets really small is going to be 0, and of course h itself is going to be 0. So we're going to have 0 over 0, but we know just physically that that slope is not going to be undefined. We're going to have a very specific value. So we're going to spend a lot of time today figuring out how do we calculate those limits so we can get the average rate of change at that point, and then in general, how do we get it for any point on that function. So this page here, this is the first part of the lecture on is one that you should be able to construct yourself and write a short paragraph on how to get to it. So in other words, you take, let's say, you say something like, take a function f, establish 2 points, make a secant line, make the difference between the 2 points closer to 0, and you get this ratio. You find the limit as h gets to 0, and you find the derivative. The very first question on the final will be define a derivative in terms of a function, a secant line, and a tangent line. There will be some words to those effect. And so the first question you will be asked then is to explain in your own words what this graph is about. So kind of circle this and keep on going back to it, because it's really one of the most fundamental things about calculus that we're learning in this class. Okay, so let's go on from here then, and let's try a few of these. I think I did a couple of them on Friday, so we'll start with where I left off. So I have this function, f at x equals x squared, and I want to find the slope of the curve at x equals 1, or the derivative at x equals 1. And so I'm going to start this out by writing my definition, the limit definition of the derivative, and then I'm going to actually write out what my function is involving 1 plus h, so it's just squared, so it's 1 plus h squared minus 1 squared over h. And then I'll expand the 1 plus h squared into 1 squared plus 2h plus h squared. And of course I have the minus 1 squared, so now it's a matter of simplifying this expression. And so I end up with 2h plus h squared over h, and now if I divide through by h, I get, the h's will cancel after I factor out the h, and then I get 2 plus h. And this evaluates, right? Now, these two, back in the way we're thinking about limits, this expression and this very first expression that I used here, they're equivalent expressions except at h equals 0, right? Because this one has a domain restriction at h equals 0, but we've simplified it in a way that we don't have that domain restriction anymore. So strictly speaking, it's not exactly the same function because one of them has h in the has 0 in the domain, the other one doesn't. But they're equal at every other point. So what I said about limits is that the two limits then are equal to each other. So all we do here is now realize that as h goes to 0, the limit of 2 plus h goes to 2, and so the slope of the graph at x equals 1 is 2. So if I were to draw a picture of this, here's x squared, and where x equals 1, f at x equals 1. So we have this point, and I'm talking about this tangent line here, and the slope of the tangent line here we found is 2, where the instantaneous rate of change at x equals 1 is 2. All right, so let me run through a couple more examples then. So I want to find the slope at 2 of this function where we have, this should be f at t, not f at x. Let me back up and correct that. Okay, so we have f at t equals t plus 1 over t minus 1. Okay, so I'm going to define my my derivative, f at the derivative at 2. Just write out the definition where I have f at 2 plus h minus f at 2 divided by h, and I'm taking the limit as h goes to 0. So now what I'm going to do is I have an exercise in simplifying a complex fraction. So I've plugged in 2 plus h for both of my t's here. See, one of them is plus 1, the other one is minus 1. And so I'll find the common denominator. And you can see as I simplify this first, I get 2 plus h minus 1 is just going to be 1 plus h, and then 2 minus 1 is 1. So I have this expression here. And then find the common denominator and combine things. So what I have here is I've multiplied 1 plus h times this negative 3, so I have 3, or negative 3 times 1 plus h. Still have the same numerator, but then remember also when I have a fraction divided by another number, I can just multiply the two denominators together. So in other words, if it's like this, a divided by b over c is going to be a over bc. So you're going to get a little bit of practice doing these complex fractions, so make sure you're good and solid in that. So here I have my 3 plus h minus 3h. Once I distribute that negative 3, and that's all over h times 1 plus h, and this works out to negative 2h over h plus 1 plus h. And so I get my limit as h goes to 0 equals negative 2. Now I want to make a couple comments about how I'm working this and my notation. One of the things that's very easy to do when you're solving equations is that if you're keeping the left side the same, you just tend to drop it. And right now is not the time to do that, because we're going to be flipping back and forth between doing operations on the function, on its derivative, on limits, on the expression within a limit. And so what I have here is this is my derivative, this is the definition of the derivative there, and this is the first step was to actually explicitly write the function with the substituted variable. Now what I've done here is I've started a new series of expressions, of equalities. And notice I've left off the limit. What I didn't do was put an equal sign here, because it's not equal to it. Okay, so just to write it on the board a little bit more what I'm talking about, is be careful in the notation, because if you have a limit of something and you make all sorts of operations on that something and you keep on making changes, keep on writing the limit. Okay? Now it's okay if you're going to take that expression outside of the limit and then find some other equivalent expression, but then you go back and you write, okay, this equivalent expression now is written as a limit. Do not do this where you're just going to say that equals some expression without actually calculating the limit, because this is not true. Okay, so it's going to seem like I'm a little fussy with you about how I'm going to be grading and marking things, but this is a really important thing that you don't want to, you're going to be changing from calculating limits to working on expressions to going back to calculating limits, and that's the same thing if we have a function and we're taking a derivative. Just because we're starting to take the derivative doesn't mean it's all equal. We have to write it's the derivative and not the original function. So be very, very careful about how you're writing your notation, how you're writing this out, because it's easy just to start to get lazy and drop either writing the limit or what the function is or things like that. Okay, so here what I've done is I have made sure that I'm not writing equals. There's not an equals here or an equals here, because I'm not saying it's equal. All I'm doing is I'm taking this inner expression and I'm simplifying it. Now I'm going back into my limit and calculating it. Okay, so make sure you're not overusing the equal sign. Make sure you're writing things as complete sentences. Mathematical sentences, that is. Okay, so let's do another one. Here's f at x equals 1 over x. And there's the definition there. And what I'd like you to do is I'd like you to work on this one. Let's do the same thing, only keeping x instead of a. And so notice I do exactly the same steps. And so what I get now is I'll start from up here. Here's just a basic definition that involves f. Now I make my substitution where I have 1 over x plus h minus 1 over x, all divided by h. Now what I'm doing is I'm taking that out of my limit expression, and so I'm just manipulating this expression here. I'm going to take a common denominator, so now notice I have an x here and an x plus h, so my common denominator is the product of the two. And so I have negative 1 times x plus h and then 1 times x. And so I get this expression, and so I'm careful with my signs, and so I say x minus h over this, x times x plus h. And so I'll I'll take, simplify the fact that x minus x is 0, and then I'll make all the denominators into one product, and I have an h in the numerator, h in the denominator, so those cancel out, and I get this expression. So these two here, what I started with and this one, are equivalent expressions, except by dropping the h here, I'm avoiding that domain restriction that says I can't divide by 0 when h is 0. Okay, so I put it back into my limit expression, and notice I have a negative sign in front of here now. And as h goes to 0, then this just becomes x. And so I have negative 1 over x times x, which is negative 1 over x squared. And so my derivative is going to be negative 1 over x squared. Okay, so now let's look at this in terms of our graphs again. So if my my white chalk is going to be the function, let's plot the derivative now. You know what negative 1 over x looks like. 1 over x is like this. You know, both on the negative and positive side we have the positive curves. But since I'm taking the negative, it's going to go like this. Okay, so there's not too much contrast there, but my orange is going to describe, that's the function, that's the derivative of the white chalk, which is x. So go back to where we had 1, and we said, okay, what's the slope here at 1? We said it's negative 1, so of course, right there on the graph, it'll say negative 1. So as we get closer and closer to 0, we get a smaller and smaller negative number, and that's what we get. We get a more extreme negative slope. As we go out greater than 1, we'll see our slope gets closer and closer to 0, but won't actually get to 0, and that's what this function describes, that as x gets larger and larger and larger, it gets closer and closer to 0, but it's always slightly negative. And we can do the same thing over here, where if we look at negative 1, for instance, the slope here will still be negative, and it looks like it would be negative 1, and indeed that's what the graph should tell us. And I think I've made a little nicer plot to show you how this works. So we have now the function and the derivative of the function. So look at this point over here where x equals negative 1. We have both the derivative and the function's value equals negative 1. Okay, any questions at this point? Okay, so let's go through a couple more examples. So here's a function. X squared minus 2x, and I want to find the derivative of this function. So the first thing I'm going to do is lay out what my definition is, f at x plus h minus f at x divided by h. And then I'm going to substitute in the function. Careful that I make my substitution correctly. I'll give you a minute to catch up on this one. Now with this one I don't end up with a complex fraction, but I do end up with a polynomial that's as long as the page is wide, about. And so expanding that x plus h, and then distributing the negative 2 and that negative sign in front of my function, I get all my my terms. And then the next step, I'm going to collect all my terms. So I end up with 3x squared h plus 3x h squared minus 2h over h, and then I can cancel out all my h's in there. I get 3x squared plus 3xh minus 2. And so as h goes to 0, that middle term, that 3xh, goes to 0, but the other two terms in it stay put, so we have 3x squared minus 2 is my derivative. Excuse me?
What happened to the middle term?
The middle term, remember we're taking a limit as h goes to 0. So as h goes to 0, 3xh turns to 0. Okay? And this one, of course, doesn't involve the h anymore because the h is canceled out. Now you have to be really, really careful on how you simplify these fractions. It's an easy mistake just to cancel 1 or 2 terms and not do the whole thing. In effect, what you're doing is you're factoring out an h and then dividing by factors. Cancel your factors, don't cancel terms. Okay, so it's a shortcut to do it term-wise like this, but make sure you understand that every term has to have the h in it for you to divide through by h like this. Now it seems like a lot of work, and it is, and we're going to end up with some rules that will make this not so much work. But right now, this is the way I'd like you to do it. When I give the directions, use the limit definition of a derivative to find the derivative. This is what I'm talking about, is using this definition to find the derivative. We're going to have rules that makes this particular one almost trivial once we get into it a little bit. So anyway, that's what that is. Okay, so let's talk about notation a little bit. I've used the f prime for derivatives, and there's several ways to write it. Okay, so if I have f at x equals y, let's say this is my function, I have several ways to write my derivative, and you'll find that writing it in different ways in different circumstances is helpful. And so we have some equivalent expressions. So the first one is that we can put the prime right after the f. You read that as f prime of x. That's the derivative. So that's the function that describes the slope of this function at any given point. And notice I can put my y prime like this too. So now I'm using functional notation without the variable in it. So when I say y prime, I'm implying that y is a function and that I'm taking the derivative of the function. And this is perfectly fine. And if you get up to, well, into Math 28 and beyond, where you're going to start talking about some differential equations, you'll be notating some functions like this, because it's a whole lot simpler than always writing y at x or whatever like that, anything like that. So that's a perfectly good way to write it. The other way, and we'll talk a little bit more about differentials as we get into derivatives, you can write it, and this is what's called Leibniz notation, after the guy who developed it. That d is not a variable. That d dx is what's called an operator. So that means that we're taking the derivative of y with respect to x. And this is a handy notation because once we get into integration, we're going to use the numerator and the denominator separately. And but the meaning is still the same. It's the derivative of y with respect to x. You can also write it with just the function name, so df dx means exactly the same thing. And then you can write it with this d dx operator in front of the full definition, and sometimes this is useful because you can then, in parentheses, write the full expression for f at x. And then something that I don't use in this course is the capital D operator, although I probably should change this to say it's used in your textbook. So you will see something with the capital D, df, or sometimes dy, and that with the capital D, that means the derivative of this. All right, so that's D is not a variable; it's an operator. That means that it's taking the derivative of the f or the y. So when you read your textbook, and I hope you're following up on the textbook, I haven't assigned things explicitly in there, but it's following the sequence of the course. So it's a good place to get an alternate explanation. Okay, and one of the things to realize about this differential notation, what this really means, it's the change in y divided by the change in x as the change in x goes to 0. So this is essentially the same definition that we have before with limits, but this is now suggesting symbolically that we're taking this, this secant line and bringing the two x's together. That delta x, becomes very, very close to 0, and we get that slope. So this one really suggests, this the way we started out with talking about derivatives. And then a couple other ways to notate it is that if we're going to evaluate the derivative at a particular value, we can still write it in other forms and either use a straight line or a bracket and write x equals a. So what this means is the derivative of y with respect to x when x equals a. Okay, so when I was looking at calculating these, I could have done the same thing by saying dy dx evaluated at x equals 1. And when we get into definite integrals, we're going to be using a notation similar to this quite a bit. It's just a nice way to put a value in here, and retain what the expression, the notation that you are working with the derivative. It's a nice way to retain that. All of these are used in the course, but you won't see me doing this because I'm officially old, and these things come in trends and fashions, and when I was in school, we never used that, so I never use it just out of habit, but it's in the book. I will most certainly be using all of these forms up here, okay? This one is more or less a way to think about what dy dx means, okay? And then this we'll use mostly in integration, okay? So you should be comfortable reading all of these. I mean, this notation with the capital D in there is it's used regularly, but a lot of it is just habit, what you tend to use and things like that. I mean, it doesn't confuse me when I read it. It's just if I'm writing something, I hardly ever write it that way myself. Okay. So let's get into a couple definitions here. We're going to call a function differentiable at a if the derivative at a exists. Okay, so with my example of 1 over x, we took the derivative where x equals 1. So we can say 1 over x is differentiable at 1. So we're kind of using the word differentiate as a verb now. And then we can also talk about being differentiable on an open interval if it's differentiable at every point in the interval. So if we look at this particular function, the 1 over x, it's not differentiable at x equals 0, but it is differentiable from, on the open interval, 0 to infinity or 0 to negative infinity or negative infinity to 0. Okay? So we have some place that we don't have a slope, so we can't say it's differentiable there. Okay, so now here's a question that frequently comes up. Remember my comment or my really bad joke on Friday about mathematicians are worried if something exists or if there is a solution or if the solution is unique. Very often you want to say, does the definition apply to certain functions, or do we have certain properties in certain circumstances? So this is a perfectly good calculus kind of question. Is the absolute value of x differentiable? Okay, so what that means is that it has to be differentiable at every point. Now, if x is greater than 0 or if it's less than 0, the slope looks just like a line. So we would imagine that 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 it is differentiable everywhere, but we don't really know 0 yet. Is it differentiable there? So here's what I'm saying, that if we look at x being positive, then the absolute value of x is just x. And so if we use the limit definition, what we get is the limit as h goes to 0 is 1. And so when we have our absolute value function, remember it looks like this. When we're not at 0, when we're over here, the slope is 1. Okay, you can see that from a graph, but here I've just shown by the limit definition that it does equal 1. If it's so we'll say that this function is differentiable on the open interval from for any value that's greater than 0. So when it's less than 0, we have f at x equals negative x. And so if I do the same thing, we come out with a slope of negative 1. So here the slope is negative 1, and so we would expect everywhere where x is 0 that the derivative is going to be negative 1. So what is it now when x equals 0? Okay, so at x equals 0, if we put this in our limit definition, we have the absolute value of 0 plus h minus 0 over h. That's just putting in by the limit definition of the derivative. And so we get the limit as h goes to 0 of the absolute value of x, the absolute value of h over h. Now we did this before. Remember when we were calculating limits, is the absolute value function divided by x, does that limit exist? But we know that it doesn't exist, because if we come from the left, it's going to equal negative 1. If we come from the right, it's going to equal 1. And since the two limits don't exist, we know that it's not differentiable at 0. Okay? So we look at this and we think, okay, what's the slope of this particular graph at 0? Well, there's no unique tangent that sits there, right? You could make an argument for any value, that it could be many values, and that's not right. It's a particular value. And so it does not exist at x equals 0, the derivative, so it's not differentiable at x equals 0. Now we also said, though, that this was continuous, right? Every real number has an absolute value. So here's a very important thing to remember, that not every continuous function is differentiable. So think about that. Not every continuous function is differentiable. That means that you could find the derivative of the function at that particular value. So this is not differentiable at 0, because no derivative exists. Okay? It exists everywhere else because we can find the derivative at any other point. So as a function, this is differentiable on the intervals negative infinity to 0 and 0 to infinity, but it's not differentiable at 0. Okay? Okay, so this is what I've been saying here. So we've seen that not every continuous function is differentiable. Now let's think about the other way around. How about the other way around? Is every differentiable function continuous? Okay, here's a theorem. If f is differentiable at a, then f is continuous at a. Okay, so here this is not differentiable there. But if we have any other function, if that exists, then you must have a continuous function at that point. So remember, let's say we have a function that is not continuous at a particular point. It's not going to be differentiable there. And you say, wait a minute, that's what we did when we took the, we got around that by using our limit definition of the derivative. The limit exists going to that point, but the point itself has to exist. If you look at the definition, the limit as h goes to 0 of f at a plus h minus f at a over h. So this is the definition of the derivative at a. So if this exists, this has to exist, this has to exist, and this has to exist in order for the limit to exist, right? And so f at a has to exist, and it has to be equal to the limit as h goes to 0. Well, we're just talking about a particular point, so that's a value that's not going to change with our limit, so it must exist. Now, there are formal proofs of this thing, and I have given them in class before, and it's a kind of a long, tedious proof, and I don't know that you get anything more out of it. The real gist of the proof is that if this thing exists, then it's continuous, right? And if it doesn't exist, it's not continuous. And this has to exist for this to exist. All right, so if we know that we have this value, that infers that we have this value. Okay, so it's not the other way around, that a function can be continuous. This can exist without this limit existing, but in order for this limit to exist, this must exist. Okay, so it's kind of like, if I'm in Paris, I'm in France, but just because I'm in France doesn't mean I'm in Paris, kind of a deal. So here's one of these things where one of the ways that we can prove a function is continuous is to prove that it's differentiable, or find its derivative. If the derivative exists, then we know that the function is continuous. Okay. So where are functions not differentiable? Let's look at this a little bit more broadly now. We have essentially three different scenarios where we don't have a where it's not differentiable. One is at a corner, like our absolute value, or if that corner exists in any other fashion, this may be continuous, but it's not differentiable, because this thing, the limit of this line, the secant line that we would get coming from this side, is going to be different from the slope of the secant line coming from this direction. And so since they're not the same, when we're at this point, we don't have that, the limit doesn't exist, and so we don't have the we don't have a differentiable function. Now, if we have a gap like this, a discontinuity, a function must be continuous in order for it to be differentiable. So if we have one that's clearly not continuous, you can imagine, well, the way I've drawn this, it's possible that it could be the same slope, but you can imagine that the slope of the line as we get closer to this point doesn't necessarily have to be the same as the slope as we approach from the right. But here again, we get into this, this notion of the limit again, where that limit has to be the same coming from both directions. And when we have a gap there, it's not going to be the same because the limit, as we get closer, as either from the left or the right, that we don't end up in the same place. And then finally, the last place is if we have a tangent that is vertical. Okay, so it's possible that this curve has a tangent, like let's say take a semicircle or a circle and you put up a tangent on one side or the other. That's not differentiable at that point, because when you think about what the derivative means is that it is equal to the slope of the line tangent at the point. And so if we have a tangent that has a vertical slope, whoops, that's not extreme enough. If this tangent is like this, the slope of this line does not exist. So if the slope doesn't exist, the derivative doesn't exist, because that's what the derivative is. It's the slope of the line that's tangent at that point. Okay, so to contrast these, we have, this is continuous but not differentiable. This is not differentiable because it's not continuous. And here's one that's continuous, but it's not differentiable because the slope does not exist for the tangent. Okay, so it's possible also that we think about higher derivatives. And so the easiest one to think about is the distance function and its derivatives. So let's say f at x is a distance at time x. So I'm driving to work, or I'm driving into school here, and I'm going down 680, and I'm at a certain position. So at a certain time, I'm at a position, so my function exists at a certain time. Now, my rate of change, the velocity that I'm going, is going to be the first derivative, right? So the rate of change of my distance is my velocity. So I look at my speedometer and I see that I'm going, since I'm a law-abiding citizen, I'm going well within the speed limit, so I'm going by 55 miles an hour. And so I can describe my velocity as the derivative of the distance function. Now, it's possible that my velocity is changing. I could either be braking, or I could be accelerating, or coasting to a slower speed, or going down a hill and increasing speed. So the rate of change, of the velocity, and we notate it by having the double prime here, is going to be the derivative of the derivative. Okay, so my second derivative, and this is the way I'm going to notate it, is this d, I even hesitate to call that a squared, but it's d squared y over dx squared. And it's important to put these squareds in different places, because remember the notation dy dx, if I use the derivative operator here, notice I just have a d here and a dx here, so this becomes d squared dx squared. So this is the second derivative in motion studies. If my function is the distance function, my velocity is the first derivative, my acceleration is the second derivative. Now, of course, we can keep on making rates of change. My acceleration can be changing with time too. Like if I apply my accelerator really hard and then back off a little bit, I'll be accelerating more quickly at the beginning, but we normally don't talk. We don't have a nice word for that. Like the second derivative is acceleration. There's no real rate of change of acceleration word that we use, but it comes up in different places in math where we will be taking successive derivatives. We're only going to be looking at the second derivative because that's going to have some meaning in our graphs and in interpreting what certain graphs do. Okay, so the rate of change of velocity is acceleration. Now, if I'm going to do this, this is the square of the derivative, okay? So if my derivative is 2, 2 squared is 4. If my derivative is 2, I know nothing about my second derivative without having a little bit more information. So these two, I suppose they can be equal, but they don't mean the same thing. Okay, this is the square of the velocity. This is the acceleration. All right, so we have to be careful with, just like with functions, remember we were talking about inverses as being this, and we want to notate this as being different than 1 over f at x, which is going to be f at x to the negative 1. These are not equal. Same thing with this notation. We have to be careful that when we're notating the second derivative that we do it in this fashion, not in this fashion. Okay, and I think I'm almost done here. We can do higher derivatives, and once we have about 3 primes on there, it gets a little ridiculous. So what we do is we put the number of derivatives in a parenthesis. So this means the 4th derivative here, because we have the parentheses. All right, so it's just a little notation thing. We won't be getting into the 4th derivative in this class, although theoretically there's no reason why we can't calculate it. It's just not going to be of any use for the kinds of things that we're going to be talking about here. Okay,